Bismillahirrahmanirrahim. Assalamu alaikum dear students. Welcome to the online lecture on Matlab simulation of nonlinear control. Today we are going to discuss guidance law against maneuvering targets with intercept angle constraint. In this paper, a guidance law has been designed using terminal sliding mode control. So we shall see how this guidance law can be simulated using Matlab. The paper presents that the limitation of traditional guidance law, which simply treats the unknown target acceleration as zero, that has been analyzed in this paper. A linear extended state observer is constructed to estimate the acceleration, and that we will also implement in Matlab. And to avoid the singularity in the terminal phase guidance, the sliding surface has been designed with the non-singular terminal sliding mode control scheme, and they claim that also, this is not just a claim, they also show using the graphs and comparison that more accurate intercept angle can be achieved using the guidance law that has been designed in this paper. So as usual, we will not go into the details of the paper, we will just focus on the mathematical model. So this is the scenario where you have a missile and this is the target, and r is the distance between the target and the missile, and there is missile heading angle and target heading angle, and then there are some velocities of the missile and the target and some accelerations as well. So these are the dynamics of the system. The rate of change of the range is given by the target velocity times cosine of angle, cosine of the difference between the target angle and the line of sight angle. Lambda is the line of sight angle, and then there is this lambda dot, the rate of change of line of sight angle, that is given by this equation. And then there is this missile heading angle, the rate of change is given by this equation, and this is the target heading angle. So this is the description of all the variables in the paper. And then we have these are the dynamics. This is the double derivative of the line of sight angle, which captures the whole dynamics of missile trying to chase down the target. And then we have this desirable angle, like the desirable value of the line of sight angle. When the missile and the target are on collision course, the respective speed perpendicular to the line of sight is zero. So from this equation they have obtained this lambda sub ff, which represent the desirable line of sight angle when the interception occurs. So the whole idea is to achieve the desirable value of the line of sight angle given these dynamics of the line of sight angle. And the guidance law will be basically determining the AM, this acceleration of the missile will be determined by the guidance law. So before the guidance law is designed, a sliding mode control and extended observer is discussed. Sliding surface for terminal sliding mode control, the usual sliding surface is given by something like this: x plus beta times x dot raised to the power gamma, or sometimes it is x dot plus alpha times x to the power eta. So both type of sliding surfaces are used in the literature, and they are basically equivalent to each other. Both of these 14 and 15 are equivalent. Then there are some remarks in the paper and so on. We will not we don't need to go into the detail of that, but we do need this observer, so because we need to estimate the target acceleration and similar things related to the target. So basically the guidance law is designed in this. So first of all, let me So this is the observer, and so this is the main equation, the generic equation of the observer, and this is the equation of the observer for missile guidance system, where z1 dot is equal to z2 minus beta 01 is this just a parameter. So this v lambda is basically this is the lambda dot times r. It is defined above. So we are estimating v lambda, and based on v lambda, so this is v lambda r times lambda dot. So basically we shall be estimating lambda dot, and v lambda will help us in that, which is the rate of change of line of sight angle. And then z2 dot is equal to beta 02 times e1. So these are the equations of the estimator. And then this is once you estimate, once you have the states z1 and z2, you can get the target acceleration from z2 divided by cos of phi t minus lambda, where phi t is the heading angle of the target and lambda is the line of sight angle. Similarly, this is the proposed guidance law by this paper, and this is what we will be implementing using Matlab. And then there are some initial conditions and parameter values that are given in the paper. So without further ado, we can just go straight to the code. This is the Matlab code for this whole system presented in the paper. So you can see here that first of all we have written the values of all the constants that are given in the paper, and then there is this equation of lambda f. This lambda f equation is right here. If we compare side by side with the paper, so this is the lambda f equation 11, or basically I have implemented this modified form of lambda equation, lambda f, which is given somewhere around here. So let me, okay, so this is the equation. Let me zoom a little bit. So this equation 44, that is the equation. There's a little bit modification in equation 12. So the authors suggest that we use this equation 44 for lambda f, which is here on line number 4 in the code. And then we have this equation x7 of divided by cos of so x4, remember. So let me tell you what are the state variables in the system. So remember these equations. So equation 1 2 3 4, so r will be our first state variable, which will be x1, and x2 will be lambda, x3 will be phi m, and x4 will be phi sub t in this code. So x7 is basically let me tell you what x7 is, but before I tell you that, x4 is phi t, and x2 is equal to lambda, which is the line of sight angle, phi t is the heading angle of the target. And then I have so these are the first 4 states. R is x1, lambda is x2, phi m is x3, and phi t is x4. Then since in the missile dynamical equations we have lambda double dot as well, so lambda double dot, so lambda dot, the first derivative of lambda is x5. So my fifth state is the first derivative of lambda. So the derivative of the fifth state, the derivative of x5 will be equal to lambda double dot, which is this equation, and this equation is the same as equation 7 in the paper. again here r dot is this is r dot. R dot, you in this equation you can get r dot from here, but instead of getting lambda dot from x2 sorry, this is r dot, this is r dot, which is the same equation as equation number 1 in the paper, and this is lambda dot calculated using equation number 2. But since the fifth state itself is lambda dot, so x5 will also be lambda dot. So you can get lambda dot from the fifth state. The integration of this part of the differential equation will give you lambda dot, and you can also get lambda dot from the derivative of lambda. Okay, so and then this is the fifth state, so fifth state is lambda dot, and now state number 6 and 7 are z1 and z2. So z1 and z2, remember that these are in the observer. So if we go down from here, so z1, this is the first state of the observer, which is state number 6 in our case. This is z1 dot. This equation is the same as if you look at the paper, so this is equation number 31. So this is given so this is translated into code as x6 dot and x7 dot. This is x7 dot is basically z2 dot, and then we have this term z2 c1 is x7 divided by cos of x4 minus x2. This is used in the sliding surface. So if you look at the sliding surface equation in the paper here, I think that would probably be, yeah, this equation. So the sliding surface is given by lambda minus lambda f plus beta times this whole thing, and so this equation 33, that is the sliding surface, this is implemented here, and this z2 c1, this z2 divided by cos of phi t minus lambda, that is used in the sliding surface. Then we have some other terms that are used in the guidance law. So for example, z2 over cos phi t minus lambda, that is also used in the guidance law as well. This is the guidance law. So guidance law is a little bit lengthy. You can basically pause the video here and copy this whole code, except that there is some missing terms in the guidance law. So I will slide the file over so that you are able to see the remaining part of the guidance law, and then you can basically copy this code from this video, and then so this is the whole code for you. So once again I slide this again so that you are able to see the whole statement of the guidance law. So this is the guidance law. So implementation of the guidance law is not straightforward. We have applied some saturation mechanism on it as suggested by the authors in the paper. So you can see here that the author suggests that you apply this saturation mechanism on the guidance laws, that the AM should be, there should be a value AM max. If AM is greater than AM max, then you just use the AM max value instead of the AM value, and if it is less than the max, then use it as it is. So this if AM is greater than AM max, then I just use AM max and into sign of AM instead of the AM suggested by the guidance law. Then again, starting from the beginning, these are the lines, these are the constants. This lambda f is equation number 44. Then this is the sliding surface, equation number 33. Then there is okay, so then there are some inside the guidance law. There is this sigmoid function, which I will let me show you here. Here they have suggested that, you know, this function, sigmoid function of the sliding surface, which is used in the guidance law, it is used here at this position. Oh, at this position. So this should be implemented with you know, some, if its absolute value of s is greater than epsilon, like here, if it is greater than epsilon, just use sine of s, otherwise use 2 times this whole sigmoid function. And then this eta should also be used based on, you know, whether the sliding surface absolute value is greater than epsilon or less than epsilon. So that is why I have decided like eta is equal to k if absolute value is greater than epsilon, otherwise eta will be k over d eta. D eta is also given in the paper, which is this value 4 given in the paper. And so all of these equations have been implemented in the code in the correct sequence. And once you do that, then you can basically go and call this function using the ODE 45 function. And you can, all the initial conditions are also given in the paper, so I've just copied. So this r naught is given in the paper, lambda naught is given in the paper, this all things are given in the paper. But this L, the initial condition for L lambda dot, you have to calculate using the equation of the lambda dot and all the initial conditions. And then you can use that to calculate the initial condition of z1 as well, because z1 is r times lambda dot. So initial condition of z1 will be the initial condition of r times the initial condition of lambda dot. Similarly, once you have this all the state trajectories, then you want to compare them with the lambda f, then you also want to plot the sliding surface. So for that I have just repeated the code that is in the original file. The difference is that instead of x7 I will use xi comma 7 in the for loop. So that's the difference. And once again, I have gone through this video fairly quickly to save time, but of course you can pause the video, you can rewind the video, watch it again, or you know, you can pause it to copy the code and type the code by yourself, and that will give you some confidence and keep you going. So once you have written all this code, then you run the file and then you get the plots. I have just run, so this paper has presented like 4 cases, but I have just simulated the first case. And also this paper compares this proposed guidance law with other guidance laws. I have not implemented all of the guidance laws, because implementation of a guidance law and a sliding surface that requires you to change only 2 lines. So this is the guidance law, you can use any guidance law instead of this one, and this is the sliding surface, you can use any other sliding surface instead of this one. All other dynamics will remain the same. And then you have this case 1 where the target acceleration is 20. So this is what I have implemented in my code. If you look at here, I have defined at to be equal to 20. And then once I have already run this file, so I will compare the plots with the plots of case 1 in the paper. So this is the plots of case 1. If you look at so this is the comparison between lambda and lambda f. So you can see here that this lambda is approaching lambda f. So let me just this corresponds to this figure 1 corresponds to this this red line is the lambda with their proposed approach, and this green line is lambda f. So this in the green line in the paper corresponds to the dotted red line in this figure 1, and this blue line corresponds to this red line. and then we also have the estimate of the target acceleration that goes to 20. So we already know that we have set AT to be 20. The estimate of AT is of course obtained from Z2, and then that is that goes to the value 20 as expected. And then finally there is this sliding surface, which is basically, you can see here, this is the plot of sliding surface, the red line with the proposed approach. So this is the sliding surface. So I have equalized the axis to the axis in the paper, so that you can relate the two shapes together. Otherwise, I mean, for that I have used this extra command of axis. So I didn't have to use this command, but I used it just to make it, make the axis of this figure equal to the axis of this figure in the paper, so that you can relate easily, relate the two figures quite easily. Similarly, you can plot other things that have been plotted by the paper. The purpose of this video is just to keep you going on usage of sliding mode control for the missile guidance. So guidance law against maneuvering targets with intercept angle constraint. So I hope that this video will help you in doing your own research on the same topic. Once again, at the end, this is the code of the file that calls the function which has all the dynamics, and this is the code of the file which has all the dynamics. So in this shot of the video, you should be easily able to pause the video, take a screenshot, and type this code by yourself and see what happens. And similarly this second file as well, and then from here on you can carry on your own research. Thank you for watching this video. You can subscribe if you want to get notifications, or if you are interested in more videos related to the research papers or MATLAB simulation of control systems, or theory of the control systems in itself. Thank you once again.